In this lecture, we are going to see the topic that is related to the analysis of proper cantilever beam subjected to a moment at the roller and support. Coming to the question, here you are going to determine the reaction components for the proper cantilever beam that is subjected to the moment at roller and support as shown in figure, and draw shear force and bending moment diagrams. So this is a proper cantilever beam AB, and it is having a span of length L, and at the roller support we are having a moment that is acting. So before determining the reaction components, first you are going to determine the degree of static indeterminacy. So here at the A support, as it is a fixed support, you are having a three reaction components. That is, one is horizontal component HA, and another is a vertical component RA, and another is a moment that is MA. And at the B support, as it is a roller support, you are having RB as a vertical component. So total number of reactions here are 4. Now to solve this 4 reactions, we should have the static equilibrium conditions also. So here the number of static equilibrium conditions are only 3. That is sigma fx 0, sigma fy 0, and sigma mxy equal to 0. Therefore, the degree of static indeterminacy here is number of reactions minus number of static equilibrium conditions. That is 4 minus 3, it is 1. So to solve this one degree of static indeterminacy, we are going to make this entire proper cantilever beam into a determinate structure first, and then we have to solve step by step. So before making that, I'm just balancing the forces. That is sigma fx is 0. That means as there is no horizontal load acting here, HA is 0. Similar way, sigma Fy equal to 0 and Ra plus Rb will be equal to 0 as there is no vertical load acting on the beam. So this is an equation. Now we are going to make this proper cantilever beam into two parts, consists of two parts. So one part is a simple cantilever beam which is having a moment at the free end. And the second part is again another cantilever beam which is having a point load at the B support. That point load is acting vertically upward as you are having a roller support at this B end. Therefore, I am considering the vertical reaction RB as a redundant force. Coming to the next slide, we are going to calculate the reactions. So for calculating the reactions, what we are going to do is we are going to take one consistency condition. So that consistency condition is nothing but you are going to balance the deflection at this end point. So that means the net deflection you are going to make it as 0. So how you are going to make it as 0 is, now I make this proper cantilever beam into two parts as we have seen in the last slide. So first part is cantilever beam with the moment and second part is cantilever beam with the upward reaction. So just I'm going to consider now first part. So due to the given loading, so as the given loading here is applied moment. So due to this applied moment, there will be a downward deflection. So this is a deflection acting. So downward deflection, the delta B is given by ml square by 2EI due to this external moment that is applied. So that is delta B I'm writing here. Then we have another beam, cantilever beam, which is having an upward reaction at this B support. So due to this upward reaction, we are having an upward deflection, which is of RB into L cube by 3EI. So as these are opposite in nature, downward deflection and upward deflection, I'm just equating those two deflections. Or you can add the two deflections, the net deflection will be 0. Anyway, we have opposite signs. Just I'm equating these two equations. So while equating these two deflections, I'm getting RB as 3m by 2l. Another equation is there from sigma Fy equal to 0. That is Ra plus Rb equal to 0. So that means Ra is opposite to Rb reaction. Therefore, Ra is minus 3m by 2l. In this case, you can make Ra you can make it in the upward direction and you can write the value to be negative, or you can make Ra as positive value and you can change the direction of the arrow to be downward. here I'm just representing RA in the same way, upward only. I'm just making RA as negative value. So I'm just taking here the same sign convention, but I'm taking the RA value magnitude to be negative. So in the next slide, we are going to calculate the momentum. So how to calculate the moment? So as we know the RA reaction and RB reaction, now I'm taking moment about B. So moment about B here is, you're having a moment of hogging nature, which is M. Therefore, moment at B will be equal to minus M. Now, moment about that I'm going to write. So RA into L, which is in sagging nature, that is positive. And MA is also positive, that is plus MA. So that means MA plus RA into L will be equal to minus M. So by substituting RA value and simplifying the above equation, I'm getting MA value to be plus M by 2. So that means whatever the sign convention I'm considering for the A support is sagging nature. So that is correct. So therefore, I'm just leaving that sign convention to be same. So MA is equal to M by 2, which is in the sagging nature. Now, after getting the moments, next step is we are going to draw the shear force diagram. So to draw the shear force diagram, first we are writing all the reactions, whatever we got, and the moment also. Then I'm going to take a section for this AB span, which is at a distance of X from the B support. So as I'm considering from the B, I'm making X as 0 and X as L. So these are the limits. So before going to that, we'll just see the sign convention for the shear force. So when we take an element and when we cut the section, towards the section, when the shear force is acting in the clockwise direction, then we consider the shear to be positive shear. When we are considering the shear force towards the section in anti-clockwise direction, then it is a negative shear. We are going to write a equation first. So shear force equation will be equal to, this RB is in anti-clockwise direction, therefore minus RB. Here moment won't be considered as we are writing only the shear equation. So the limits here are 0 to L. At X is equal to 0, it is minus 3M by 2L, and at X is equal to L also, it is minus 3M by 2L. Therefore, while drawing a shear force diagram, at B we are having 3M by 2L, and at A also we are having a 3M by 2L, which is of the negative nature. So both are on the same side. This is how you are going to draw the shear force. Next, coming to the bending moment diagram, same the reactions we are going to take, and then we are going to cut the section for in the AB, and I'm taking section from the B support, that is X, and here the limits are X is equal to 0 to X is equal to L. Coming to the sign convention, when we cut a section, towards the section, when the arrows are heading upward towards the section, then the moment is positive moment, that is sagging moment. When the arrows are heading towards downwards towards the section, then they are considered it to be negative, that is hogging moment. So while writing the equation for the bending moment, so RB is heading upward, therefore RB into X is a positive, and M moment that is acting at B is the heading downward, so that means it is minus M. So the limits here are 0 to L. When X is equal to 0, I am substituting, I get bending moment to be minus M, and when at X is equal to L, I am going to substitute at X is equal to L. That means at the A, I am getting the moment to be plus M by 2. So that means at B to A, it is changing from negative to positive. So that means at some location, I am getting the bending moment to be 0. So I'm equating the BMX equation to be 0. So by simplifying it, I got at X is equal to 2L by 3, we are getting bending moment to be 0. So after getting all these values for the bending moment and the X distance also, we'll just plot the figure. So this is an AB span, and at B I'm having the moment to be M, which is of negative, and at A I'm getting a moment to be M by 2, which is positive. And at some distance, that is from X is equal to 2 by 3, from B I am getting the moment to be 0. So this is how you are going to draw the bending moment diagram. So these are the references and textbooks. Thank you.